Hello everyone. Today in this class we are going to discuss about behavior of pure resistor, pure inductor or pure capacitor when you are giving a sinusoidal single phase supply. So if I give a sinusoidal supply to a pure resistor, what is the relation between voltage and current in the circuit? I represent here. The first one is resistor. If I give a pure resistor or pure inductor or pure capacitor. The first point for a sinusoidal waveform I can represent like this, and if we give a pure resistor to this, it will be it will be resistance or pure resistance or pure. Pure means there is no other element will be added in the circuit, that's all. So if it is a V, so V is equal to Vm sin omega t, and because of this voltage V, the current will flow in this circuit. So I can calculate this I is equal to Vm sin omega t upon R. So that is Vm by R sin omega t. So that is the first point we can calculate. And coming to the second point, waveforms. So how can I represent voltage and current? So here the voltage waveform is here. It is voltage waveform. Coming to current waveform, it is also in phase, that is Vm by R. So that will be calculated as Im. It will always less than Vm. That's why the waveform of current like this. It is current waveform. Why? Because here V is equal to Vm sin omega t and I is also again Im sin omega t. There is no phase difference. So here voltage and current I are in phase. So there is no phase difference between voltage and current when we are giving a sinusoidal AC supply to the pure resistor. Third one is Phasor representation. So if I write voltage in phase, in the same line I will also be there. Why? Because there is no phase difference between voltage and current. And the fourth point is impedance. Z is equal to R plus JX. So X is reactance. When we are giving a pure resistor, X is equal to 0, then impedance Z is equal to R only. And this can be calculated as Z is equal to V by I, that is Vm sin omega t by Im sin omega t, that is, so with this I can calculate the impedance. And the fifth point is phasor difference. So phasor difference is equal to 0. Why? Because there are voltage and currents are in phase. That's why there is no phase difference between voltage and current. And sixth point is power factor. So the definition of power factor is cos of angle between voltage and current. So angle between voltage current is 0, cos 0 it is 1. So the power factor of a pure resistive network is 1. The seventh point, very important point, power. Power P is equal to V into I. So V into I, that is Vm sin omega t and Im sin omega t. I can write Vm Im by 2 cos 2 omega t. So if we calculate the power, so V is equal to V into I, Vm sin omega t into Im sin omega t. So if you solve these two multiplication, you can get Im Vm by 2 cos 2 omega t. Okay, so these are the points we discussed for all rest of inductor and capacitor. Okay, so let's start with the inductor. So first point is diagram. So if I use sinusoidal waveform for pure inductor, if it is a representation of inductor L, so which is having inductive reactance XL, so it is called inductive reactance. So due to this voltage I can get current I. So V is equal to Vm sin omega t. Now I is equal to Im sin omega t minus pi by 2. So when you are giving a voltage Vm sin omega t, the current I is equal to Im sin omega t minus pi by 2. How it will came? So you can see here. So why it is having phase difference of 90 degrees? We already know I is equal to 1 by L integral V dt. So here 1 by L integral Vm sin omega t d omega t. If you substitute here, finally I can have Vm by omega L sin omega t minus pi by 2. So if you solve the integration, so I can have sin omega t minus pi by 2. Why? Because I can, after integration I can get cos omega t. So minus cos omega t vasundi. So minus cos omega t I can represent as sin omega t minus pi by 2. This omega t, Vm by omega L is nothing but Im sin omega t minus pi by 2. So this is the representation of current in pure inductor. So coming to waveforms, so what is the waveforms I can get? Second point, if you see here, voltage start with at 0 point. So what about current? So I will change the color. It will start after pi by 2. After pi by 2, that will be a phase difference of pi by 2. Okay, so here this is the current waveform. So from this point I can write I lags V by 90 degrees. So this is the conclusion I can make. For a pure inductor, when a sinusoidal supply is given to a pure inductor, the current lags V by 90 degrees. And if you represent phasor representation, voltage as a reference here, how can I represent? Lags means here. So I can represent current as 90 degrees. So this is the phasor representation. So phasor representation. Coming to fourth point, impedance. Impedance Z is equal to V by I can write R plus J XL. Next, phi is equal to tan inverse of XL by R. So that is the phase difference. So in 90 degrees, how can we get 90 degrees? So if it is if it is a pure inductor, it will be 0. Then it will be JXL only. It will be JXL only. Next, fifth point, phasor difference. What is the phase difference? It will be pi by 2. Phase difference will be pi by 2 between voltage and current. And sixth point is the power factor. Cos of angle between voltage and current, that will be pi by 2. Cos pi by 2 is 0. So power factor is 0. And seventh point, power P is equal to voltage into current, that is Vm sin omega t is multiplied with Im sin omega t minus pi by 2. If we solve this, we can get minus Vm by Im by 2 sin 2 omega t. So this is the equation of power I can get when we give a sinusoidal supply to a pure inductor. Okay, if you see how can I get this phase difference, I can also calculate phase difference by using this formula. Phi is equal to tan inverse of XL by R. So what is R here? For a pure inductor, it will be 0. So anything in the denominator 0, it will becomes infinity. So tan inverse of infinity, it is nothing but pi by 2. So in this way also we can calculate the phase value. Okay. So this is the scenario when we are giving a sinusoidal supply to a pure inductor. Now the next part is for a pure capacitor. Coming to phasor diagram. So sinusoidal supply given to a pure capacitor C. It is having capacitive reactance XC. It is known as capacitive reactance. It is voltage V. Because of this voltage V, the current flowing through the circuit will be I. Now V is equal to Vm sin omega t. Now I is equal to Im sin omega t plus pi by 2. So how it will plus pi by 2? So we can have, I can calculate this current waveform by using this formula. We already know I is equal to C dV by dt. From this C into, so derivative of Vm sin omega t by d omega t or dt. So I can write omega C Vm cos omega t. So I can represent omega c Vm sin omega t plus pi by 2. Okay. So in this way I can write this total Vm is multiplied with omega c is nothing but Vm. So in this way I can write Im sin omega t plus pi by 2. And the second one is waveforms. It is very well known of voltage. So what about current? The current should be started before here. So if it is pi by 2, then the current will start here. Okay, this is the current. So from this I can write I leads. Why? Because I starts first. I leads voltage by 90 degrees. 90 degrees. That is third point. The third point is phasor representation. If it is a voltage waveform, so the current waveform will be like this. So it is 90 degrees. It is 90 degrees. Okay. So this is the phasor representation. And coming to fourth point, impedance Z is equal to V by I. Now it is 1 by omega C. There is nothing but XC. J XC. Now here JXL, it is also known as omega into L. So here impedance is 1 by omega C. Here impedance that is equal to omega L. So that is the impedance. And fifth point, phase difference is again same pi by 2. And sixth point, power factor, cos of angle between voltage and current, that is cos pi by 2. Again it is 0. And seventh point, power is equal to voltage into current. I can have, for a pure capacitor, I can write Vm Im by 2 sin 2 omega t. Okay, so in this way I can write different points. So whether it is phase difference, power factor, power, impedance, phase representation, everything can be done in a single screen. So when you are giving a sinusoidal alternating supply to a pure resistor, what is the relation between voltage and current, and what is the power factor, or what is the phase difference? So these values will be calculated. Similarly, when we are giving a pure, or when you are giving a sinusoidal supply to a pure inductor and a pure capacitor, so what is the relation between voltage and current? What is the power factor, and what is the phase difference? What is the impedance? So these values are also discussed here. In the further classes, in the next class, we are going to discuss about mixed of these things when the resistor and inductor is present. So up to now we discussed about pure resistor, pure capacitor, pure inductor. In the next class we'll talk about when the resistor and capacitor is added, when the resistor and inductor is added. So when the resistor, inductor and capacitors, that is called RL network, RC network and RLC network. So when those three elements are connected in series, that is called series networks. When those elements are connected in parallel, those networks are called parallel networks. So we will discuss those things in the next class. Okay, so we have to remember 3 points. When the sinusoidal supply is given to the pure resistor, the voltage and currents are in phase. That means phase difference is zero. When the pure sinusoidal waveform is given to the pure inductor, the current lags the voltage by 90 degrees. The power factor is cos 90, it is 0, and phase difference is 90 degrees. When a sinusoidal waveform is given to the pure capacitor, the current leads the voltage by 90 degrees, and there is a small difference in the phasor representation, and the power factor and everything will be the same. Phase difference is same. Okay, I hope you enjoyed this lesson. If you like it, hit the like button. If you have any questions, you can type in chat box, or if you type in comment box. If you feel it is helpful, you can share to your friends, and kindly subscribe my channel for more videos. Thank you. Have a nice day.